Hello, my name is Gabby Clark, and for my Choose Your Own Adventure lab, I chose to analyze the motion of a falling slinky. The goal of this experiment was to observe the effects of gravity and drag on the motion of a slinky as it was dropped, and use this information to develop a model to predict its motion. The motion of a falling slinky was observed using tracker. Data was analyzed using the fundamental physics principles used to develop a computational model. Then 2 different time versus position graphs were generated, compared, and evaluated. Fundamental principles and important formulas. This lab is based on Newton's second law that states a system experiences a change in momentum, therefore a change in velocity, if there is a net force on the system. From this law, the velocity and position update formulas can be derived. The 3 forces acting on the slinky from rest include the force of gravity, the drag force, or air resistance, and the tension force of the slinky. I created an observational model of the falling slinky using tracker. Measurements were calibrated based on the height of the man standing on the left, assumed to be 1.75 meters. The y-axis was aligned with the slinky with the negative direction pointing downward. The analysis of the frames began when the slinky was fully stretched out, before the top is released from rest, and continues until the slinky is fully compressed and hits the ground. Starting the first frame at 0 seconds, the point masses were set at the bottom of the slinky while it remained motionless until it falls and hits the ground to record its direction in the Y position. Here is my tracker video. The code for the initial conditions. The spring's mass is in kilograms. I inserted the initial position from tracker, and the initial velocity is 0 since it begins at rest. G is equal to the acceleration due to gravity, and the acceleration constant for drag is calculated through trial and error. Simulation Part 1. This loop runs until the top of the slinky reaches the bottom. In this portion, the force of tension is equal and opposite of the force of gravity. These forces just cancel out, which explains why the bottom of the slinky is motionless until the top of the slinky reaches it. Simulation Part 2. This loop runs until the last observation on tracker. In this portion, drag force is included because the bottom of the slinky is moving downwards. The net force during this time includes the force of gravity and the force of drag. Here is my glow script model. Predicted versus observed position. The predicted and the observed position line up in the first part since the bottom of the slinky was stationary. Slight discrepancies in the bottom portion are due to potential errors in calculation, slight interference of other forces, and errors in the tracking points on tracker. Why does the bottom of the slinky remain stationary? The bottom of the slinky initially remains motionless because the tension force of the slinky, basically a large spring, is equal and opposite to the force of gravity, canceling out each other. Once the top of the slinky hits the bottom of the slinky, the forces at play include the force of gravity and the drag force. The force of gravity is greater than the drag force, causing the slinky to drop and compress. Thank you for watching my Lab 5 presentation.